Okay, good morning again to everyone. It's me again. So I promise not to be the one between you and lunch. So I'll try to be very fast. So actually, this is a work that I've been doing with Professor Andrei Jivkov, the University of Manchester, on nuclear reactor pressure vessel steels. He was supposed to come here to make a presentation. He couldn't come, so I am presenting. So it's essentially about the local approach, which, as the difference incorporates the measured statistical microcracks. Okay, so this is a very quickly overview. What are local approach methodologies? The Bermin model and its extensions, application in fracture toughness predictions, a more refined procedure which does incorporate the measured carbide distribution and the some conclusions. Okay. So why do we need local approach in multi-scale predictions of fracture toughness? Essentially, that's because of the breakdown in mechanical similitude between small specimens and large specimens. For example, here we have a nuclear reactor pressure vessel. The wall thickness is usually 150, 200 millimeters. And to assess the structural integrity over the service life, usually surveillance programs, they encapsulate what we call pre-cracked Sharpie specimens. So the geometry is very similar to a Sharpie specimens, 10 by 10 by 40, but it's tested in 3-point bending. So it's there is no the V notch as a pre-crack, fatigue pre-crack. So the question then is how to correlate the fracture toughness from these small specimens to large structures, and also the what's the interest in this work, the possible temperature dependence of toughness. Okay, so we know that in ductile tubular transition, this for ferritic steels, of course, especially in transition, the toughness depends strongly on the specimen geometry. For example, a deep crack, high constraint specimens with the same material, test at the same temperature. A high constraint deep crack will have lower JC values than a shallow crack. So this is A over W ratio. You can see here a schematic increase in toughness. Okay. So the conclusion is the what we call the single parameter fracture mechanics, where J is the main fracture parameter. So J only describes essentially describes the stress and strain fields. It says nothing about the material and fracture conditions. And also a continuum approach do not consider the random nature of fracture, particularly for cleavage. That's the idea behind the introduction of what I call local approach to fracture. So the earlier work of Bellarmine was a French group, 1983. The Bellarmine group introduced the concept of the probabilistic modeling of the fracture process zone ahead of practice. Okay, and where there are random distribution of microcracks, usually they are related to carbides, usually broken carbides in the course of plastic deformation, and these carbides will nucleate microcracks, and fracture of the whole component, the whole specimen, is controlled by the critical microcrack. Okay, so we can do a simple math, statistical math, and assuming also a Poisson process to describe the microcrack distribution here, and this is very important. The Bellarmine model and all other similar models to the Bellarmine model, local approach, they assume a ad hoc power law function of the probability distribution for the microcrack. This is a very strong assumption which is implied in the model. From the Bellarmine model, we can then arrive at the wide stress. So the wide stress is a very convenient parameter, fracture parameter, because it is the integral of the principal stresses over the fracture process zone. So it couples the change in stresses and the volume of the process zone. Okay. One of the limitations of the Bellarmine model is that it relies on the assumption that grit-like microcracks or carbides will form immediately as soon as yielding takes place. Okay, so the statistical distribution remains unchanged with increased loading and deformation. So to address this issue, we recently proposed a modification of the Poisson process, and then we introduced the functional formula, psi sub c, which represents the fraction of microcracks which are eligible to propagate. In other words, not all microcracks will trigger cleavage fracture. That's the idea. And then we arrive at the same form of the Webster, which is very convenient for computations, because this is an established framework, with the difference that we have the psi sub c here, and that's we proposed this model back in Bob Dodds and I in 2015. Okay, some key issues of the Bellamy model, they all wide stress type models, is the strong sensitivity to the mesh size, mesh details. We need a large data set of fracture toughness. So parameter calibration is not simple. Also, extension to other fracture problems, particularly what we are interested in now, is hydrogen beryllium cracking through this model. Okay? So one of the alternatives is to consider the actual microcrack distribution. So we do also statistical math here, and then we arrive at an explicit derivation formulation for the failure probability, which depends on the microcrack distribution. And here we are considering then the Euro material. I think many of yours in this room know the Euro material. It's the European project funded many years ago. This is similar to a standard nuclear pressure vessel ASTM 8508 reactor pressure vessel steel. So we have a large data set that tests at different temperatures, and roughly this has 500 megapascal at room temperature. It's moderate hardening material. And this is the carbide distribution for the Euro material. This was measured at the University of Manchester at Circle by Ortner, and here from this microcrack distribution you can infer the probability density function of the microcrack distribution. Okay, and however something is still missing, because this you just described all the carbides in the material. Remember, not all carbides will nucleate microcracks. And then we are again assuming the functional for psi sub c, which describe the number of carbides which become microcracks. That's the idea. So that's how we put this in the model. Okay. And for the microcrack distributions, then we are assuming a viable distribution for the microcrack size, and also a Pareto type distribution to describe the function psi sub c. We have tried other distributions, and the other distributions also work reasonably well. And a key issue also is the critical microcrack size. So this comes from a standard linear elastic fracture mechanics, where gamma is the effective fracture energy. You can find this in many textbooks of fracture mechanics. And then we're going to see that this will play a major role in predicting the temperature dependence on fracture toughness here. Okay? One of the key ingredients of the local approach is to have a very detailed finite element modeling. So this is the finite element model nonlinear analysis for the CT specimen of the Euro material here, and using the Work 3D finite element code that was developed by Professor Bob Dodds at the University of Illinois. It's an open source code. You can go to the internet and download it. It's a very fast code. Not as complete as Apple's, but I can tell you it's much faster than Apple's. And those are the measured JC or toughness distributions for this is the viable distribution for the CT at minus 154 degrees, and half CT with half inch or 12 millimeter at minus 110, Again, the 1 CT, all deep crack, okay, at minus 21, and one CT at minus 60. Okay, so there is a lot of scatter, but the distributions describe quite well the probability distribution. Okay, so these are the predictions. First, we need to calibrate the model parameters, which is not always easy, but anyway, we calibrate using the CT at minus 154, and that's because it's really lower shelf. So we are very confident about the, let's say, getting a more correct number for the fracture energy at a very low temperature. So from this specimen, we then calibrate all the other model parameters. And then we arrived at the dependence of gamma, of the effective fracture energy, with temperature. And these are the predictions. So I'm going again to show you the experimentally measured distributions. And these are the predicted distributions. You can see here that, particularly for the minus 110 and minus 91, the prediction is fairly good here, quite good. At minus 60, we are reaching the upper shelf. So actually, most of the hypotheses, particularly the weak link, which imply the Bergman model, does not work that well. But nevertheless, you can see here that a decent description of the experimentally measured data. Okay. So some final observations. So the model does appear to capture more precisely the microfeatures of the cleavage fracture. It's viable, it's more effective than the standard Bergman model. We don't have all those sort of calibration issues. However, the only key issue that still needs to be further investigated is the significance of the effective fracture energy for microcrack propagation and its potential dependence on temperature. Okay, so we are doing a lot of work now. We have 2 postdocs that are working on this for the development of the probabilistic model approach, and also extension of this model to other materials. Particularly, we have a large data set for a standard pressure vessel steel, ASTM 515, a structural steel 572, and also some fracture toughness data that was developed at the University of California, Santa Barbara, Professor Bob know that, with a standard 533 reactor pressure vessel steel. And thank you very much. We are ready for lunch.